The last application we're going to look at is water, well, really any fluid flowing from a tank. So imagine a large cylindrical tank with a cross-sectional area, capital A. And see, there's like a disc at the bottom, and the area of that disc is capital A. And then it has a circular drain, a little circular hole in it, that has a cross-sectional area, little a. Assume that the tank is initially filled with water to a height of h of 0 equals capital H. So that's the initial height. Right? Then the height of the water t seconds after the drain is opened is described by the differential equation, which is named Torricelli's law. He's Italian, or was Italian, which is h prime of t equals negative k square root of h, where t, of course, is greater than or equal to 0 because you can't go back in time before you opened the drain. And then k is equal to a over capital A square root of 2g, where g, of course, is acceleration due to gravity, which if you're working in the metric system would be 9.8 meters per second squared. Of course, a, capital A, and g, well, g is a constant anyway, and therefore k also, because k is built from those things, are called parameters. They're constants that are user-defined quantities. They're not independent or dependent variables. They're just set up for your system. And this is a really interesting thing to note. This equation says that the speed at which the speed right here, the velocity at which the fluid column falls, the height drops, is directly proportional, right, k times the square root of its height above the drain hole, because the height is how far above the drain hole you are. And if you think about this, this makes a certain kind of sense. Right, we all know due to pressure on the fluid column, from learning about pressure earlier in the semester, that there's a lot more pressure down here at the bottom. So if you imagine a big cylindrical tank, like say a pop bottle, and you punched 3 holes in it, well, that first one would leak kind of very slowly, right? It would just kind of go out at a very low angle. But the bottom one has a lot of pressure. So it has all this whole volume of this column weighing down on it. So the water is going to come shooting out, right? It's squeezed out from that height because it's getting pressed on by the weight of the water above it, right? So it's pressure. That's what this is saying. It doesn't actually have to be the bottom of the tank, although that's the way we've drawn it up here. It actually works for even being on the side of the tank. If you're interested, I've linked to, in the class notes page, the Wikipedia page for this, which has a very interesting drawing. And actually, I found a couple of people in differential equations and physics classes working on some examples and punching holes into things. So it's really kind of fun. So some of the math they're doing is a little bit past this class. It'd be more in a differential equations class. But you can see the strongest jets would be down at the bottom, the weakest jet would be on the top. And it's actually not going to last very long because the water will drop away. And in case you're interested, you can watch some people actually make an experiment of that on YouTube, which I've linked to. And of course, this would be important for the sake of hydrostatic pressure behind a dam, because that curvature would come out based on Torricelli's law. And I've linked to that the YouTube video as well. Now let's get back to the boring math part of this, rather than the fun watching people punch holes in bottles and watching the fluid drain out. So we want to see if Torricelli's differential equation, so according to this differential equation that's up above, and I just wrote it again right here just because it was so far up on the page, is h an increasing or decreasing function of time t. So height, remember, h is the height of the water. So h, let me just note, is the height of the water at t seconds. Okay, so they're asking, would h be increasing or decreasing, looking at this lovely differential equation? Well, keep in mind that the square root of h has to be positive, and k has to be positive, and then there's a negative in front of the whole thing. So if you look at your h prime of t is equal to negative k square root of h. The k, well, here, let me put this. The square root of h is positive because it has to be. It's a square root. And so is k. K is positive because when you look at a over capital A square root of 2g, that has to be positive. So this is also positive. And then there's a negative in front of the whole thing. So that means that h prime of t has to be negative, because it's a negative times positive times positive. So it will be negative. And if it's negative, what does that mean? That implies that h of t is decreasing. Because of Calc 1, we learned that if your derivative is negative, it means your function is decreasing. Which just makes sense. We're draining water out of the tank. So the height is, of course, decreasing, right? I mean, look, you pop a hole in the bottom, the height will be going down. You're draining water. So let me just say, no duh. We are draining the tank. So of course it's decreasing. All right, now presuming the tank is initially filled with water to a height in meters of h of 0 equals capital H, verify the following solution of the initial value problem. All right, so there's that verify again. So what that means is they want us to verify, so part B, they want us to verify h of t equals the square root of h minus kt over 2 squared will work in our Torricelli equation, which is h prime of t equals negative k square root of h. All right, so let's see if it works. We'll start off with h of t, and I want to find h prime of t. So h prime of t, in other words, I'm differentiating here. H prime of t would be equal to 2, so we bring the 2 down, and then square root of h minus kt over 2 to the 1 times the derivative of the inside part, which is negative k over 2. The only variable in all of this is t right here. So everything else is just constants. All right, now if I distribute, multiply here, the 2 and this 2 will end up canceling because they're multiplied. So that'll leave me a negative k right here. So that's negative k out right there, times, and then all of this part that's left, look at it. Isn't that the square root of this? So if h of t was equal to square root of h minus kt over 2 squared, then isn't this the square root of h of t? And sure enough, that works, right? So therefore we have h prime of t is equal to negative k times the square root of h of t, which is what we were asked to verify. That shows that it works inside this lovely equation. So h prime of t equals sneaky, huh? All right, letter C. So let's graph the solution. Well, I really have it over here. And now I did this in Desmos. Of course, if you were doing this by hand, you'd have to go graph it in Desmos and then draw your example on the paper. But I drew it because I just thought it'd be easier. So I have our lovely example. And it says to graph the solution, and you can see that I did it with 1.44, and I had already put in constants. You can see right here, A is equal to 0.05, capital A was equal to 1, gravity is of course 9.8, and that built my K for me right here, and then I just put the K right into the equation. So there are the parameters, and there's H, which was 1.44. Done. All right, letter D, use Desmos to graph the value, to create a graph of h of t with the values of h and a from above, but instead with a slider bar for a. And let's see what happens. Well, I did that. It's right here. So if I just pull the parameters down, I can let this be a slider. Of course, this is the area of the little hole that's at the bottom of your cylindrical tank. So there's no way it can be bigger than 1 because the area of the whole thing is 1. So it's got to go between 0 and 1. 0 and 1 themselves are kind of impossible. And then we can see what happens as we, oh, look at that, right? So here, let me make it just go one direction. So if I make it go from small values, here, small values of A, to large values of A, right? So think about what's happening. Little a is how big the hole is at the bottom of the tank. So if you have a very small hole at the bottom of the tank, it takes a while for the tank to drain. But if you have a very large hole, then it's going to drain really quickly. And of course, the height doesn't go back up. That's just a factor of how this is graphed, right? So the height actually stops right there at the bottom because then you've emptied the tank. So the larger the hole is at the bottom of the tank, the faster it's going to drain. There, I just solved that problem because I basically said that nope, t can't be any greater than that value. So if that's the case, you can see it drains really fast. If I make it a very small hole, it's going to take it a while to drain, but very large, it goes quickly and drains fast. Okay, so I just wrote that. So, and it occurred to me that we should have in part C labeled our axes. So this is T and this is H, and the graph should really stop right there because we're ending it, because the water is all drained out at that point. All right, so if A is small, then H decreases slowly. If A is large, H, the height, decreases quickly because the size of the drain hole is affecting the speed at which the height of the water decreases. In other words, how quickly the tank is draining. Now, for part E, we could do this a little bit cheekily. So let's see here. They want to know after how many seconds the tank in part C is empty. Well, I'll do you one better. I just want to know when it's going to empty. So when will the height, so empty would imply the height is equal to 0. Okay, so h of t, which was equal to the square root of capital H minus kt over 2 squared, has to be equal to 0. And it wants to know when this will happen. So t when empty. So height equals 0, what's the t? So I'm going to solve this equation for t. Of course, I can square root both sides, but the square root of 0 is 0. So that just means the square root of h minus kt over 2 will be equal to 0. So I'm going to add kt over 2 to the other side. So square root of h equals kt over 2. Solving this for t, I would get 2 square root of h over k is equal to t, which, by the way, is what I put into Desmos when I graphed it. See right here, I said I want t less than or equal to 2 square root of h over k. That'll make it stop right there. And we can see that the answer is going to be 10.842 if we have 0.51 and 9.8. So how do we get that? Well, you can just substitute in the values. So this is true for all tanks, right? And then for the particular one we're looking at, for part C, for the tank and system in C, right, the water system and all that, we would use 2 square root 1.44 over k. Oh, k is, oh, I better find k. K is equal to, there's a little formula right here. It's little a over capital A square root of 2g. So k is little a over capital A square root of 2g. That would be 0.05 over 1 square root of 2 times 9.8, which would be equal to, I actually have it in Desmos. Oop, grab the wrong thing. Desmos. K is equal to, right here, 0.22136. Well, 136. So 0.22136. So that means that T would be, I just lost it. I changed it. Oop. Sorry, I'm having issues with my thing. There it is. Okay, so that means that T is equal to 2 square root of 1.44 over 0.22136, which would be about 10 point. Let's go grab that Desmos. Let me do it correctly this time. All right, so T would be about 10.842. And if you don't believe me, I can just type in the formula, 2 square root of h over k. Sure enough, it's 10.842. It's exactly where the graph ends. And it'd be seconds. So it'll only take 10.8 seconds to drain this tank.